Hi, friends. Welcome again to another episode of Beyond the Clouds Edge to Edge Transformation. And as always, it's a joy to meet with people and listen to them. I got to know David Fritz in the process of recruiting him for our, for our executive panel at the Design Automation Conference. And it's amazing how much you can learn from a person in just this one activity of doing something together. So, David, the rest of us don't know you well. Tell us a little bit about your story. How did you get here?
Sure. Well, most people don't know I'm a farm boy from Indiana, so
Wow.
I have very simple roots. Um, Graduated from college and went to work for Texas Instruments in Dallas, and I was there for a few years and had an opportunity to start my own company. So I started a company just a few years out of school. It's called Production Languages Corporation in the Dallas-Fort Worth area. Grew that company and ended up selling it to Zilog at that point. And Zilog adopted the technology that my company developed. They made me vice president of technologies for a few years. And then after that, I went to work for ARC International. At that point, I was a VP of technical marketing and got to know a lot of people in Silicon Valley, competing against the likes of Tensilica and ARM. Got to know a lot of people at ARM at that point in time, and really enjoyed my time there. After being at ARC, I got an opportunity to be the CEO of a company that's a spin out of University in Manchester in the UK called Solistics. Again, made more friends there. It was really an interesting time because Solistics was doing clockless on-chip interconnect. So it was asynchronous, and that was a new technology that, again, we thought were going to take off, but like a lot of others, it just was very hard to push something new into an ecosystem that was pretty much entrenched. And after that, I thought it was time to get back into technology a little bit deeper. So I had an opportunity to become a chip manager at NVIDIA. At that point in time, I could leverage my relationships with people at ARM. And interestingly enough, I was there for a couple of years and I got a phone call from one of my buddies at my first job at TI, who was at that point in time at a very small company. You may have heard of it, called Qualcomm. And he calls me up and he says, Dave, I hear you're helping the competition. We can't have that. So after about a year of interviews, they finally talked me into moving from Silicon Valley down here to San Diego, where I live right now. And there I was on Murthy Renduchintala's team and really enjoyed working with all the people at Qualcomm who I still have good relationships with as they kind of spread to the wind. And I was there for a while, and I was contacted by some of my friends at Mentor Graphics, that is, and they said, hey, all the work that we did at NVIDIA and everything going on at Qualcomm, we need somebody to help us formulate those ideas into a new product that we think is really going to be a big game changer. So after some consideration, I contracted with Mentor for a year. At the end of that year, they said, hey, look, you have all this knowledge. I wrote the technical requirements document, the engineering requirements document, the marketing requirements document for that product. And so they decided to bring me on full time. And I was actually at Mentor about 30 days before they were acquired by Siemens and became Siemens EDA. At Siemens EDA, I'm a vice president of hybrid and virtual systems. Hybrid meaning, part hardware, could be physical hardware, could be RTL, and part simulation. And that's what brings me to my main muse these days, and that's Pave 360. Pave 360 is really a methodology and a set of tools wrapped around that to be an environment that that addresses the complex issues all the way from SoC architecture and design, software architecture and design, and then system level architecture and design, and brings all that together with this common thread of different fidelities of simulations, all the way from pure virtual, which sometimes people call a virtual platform, to the hybrid, which is part RTL, part virtual, all the way to full RTL systems running at high speeds and producing printed circuit boards and enclosures, things like that from the simulations, and then actually physically put them into, in this case, a vehicle. So that's what we do. It's a bit like boiling the ocean, but it is a whole methodology change that I think it has undergone this transition in other industries. However, automotive is by far the most complex and the most challenges, and that's why I really enjoy it.
You know, you are not the first farm boy I've met who got into technology. And there's a series of couple of them at least. Robert Noyce came from rural Iowa. And Pat
Absolutely.
Gelsinger, the current CEO of Intel, came from, again, a farmland.
Yeah.
What is it that is in the DNA of farm boys or farm people that makes you entrepreneurs and work towards something very interesting and complex, like being an entrepreneur in the technology arena? Any idea?
Excellent question. Nobody's asked me that before. Great question. So here's how I look at it. If you're a teenager and you're spending your summers with your shirt off and a pair of jeans, throwing 40-pound bales of hay in 90 plus degree humid weather onto a trailer to make a few dollars a day, is a real motivator to do something different. I didn't even see a computer until I was in college. I didn't really know what that was about. But I have to say, I took my first computer science class, and it was like breathing. It was like obvious. And I couldn't understand why other people struggled with this. It was so simple, so natural. And it just kind of, sprung from there. So, then, majoring in mathematics and computer science and electrical engineering all at the same time, and seeing that transition and building my own computers from components and all that. And it just kind of, springboard from there. Can I tell you a story? And feel free to use the story. I'm hoping that my old college roommate doesn't ever hear this. So I was in college, I played tennis. I played tennis in high school as well. And of course, Indiana, I played a lot of basketball, but tennis was my thing in college, along with this technology stuff. So, I built my own computer. I think I was just a sophomore in college when I built the computer. And my roommate was a football player. And he would have his friends over into our dorm room pretty much every Friday or Saturday night. And, they would just do guy stuff. And they saw that I created this game. It was like Frogger. So it had frogs, except they were in their lanes and they raced like horses. And so they said, hey, let's start betting on the horses. And then it just kind of dawned on me that, you know what? If I made frog number 3 win every prime numbered race, I could probably clean up with these guys and they would never figure out what was going on. So that's what I did. And I'll tell you what, I very often paid for my books for next semester by winnings, because I know frog number 3 always won on a prime numbered race, and they never figured it out.
Wow, because of the unpredictability of prime numbers.
They never figured it out. So they just thought I was very lucky. And of course, I would lose plenty before then, but I would always get it back.
This is interesting. You did a string of startups from the
Yes.
very early one, which is the one you sold to Zilog. I still remember
Yeah.
Z80, I think was one of their first processors.
Absolutely.
Then you were at Arc International, again,
Yeah.
making processors, competing with the big boys, x86 and ARM.
Yeah.
And I think finally Synopsys acquired it. And then you were with NVIDIA and all. But at some point, you said, okay, I will do things in big companies. What was the transition like, being a startup guy and then going into large companies in technical and non-technical roles?
I really enjoy the speed that startups can move. They're motivated to create. I like the fact that people in a startup are willing to go the extra mile, to come in on the weekends and work if that's what's required, and the excitement of getting a customer and delivering to the customer, things like that. And when I transitioned into larger companies, it was very different. You know, I remember very clearly being in Murthy's office when I was at Qualcomm and simply saying, Murthy, you know, a lot of times I would just text him messages in the middle of a big meeting. And I still have people at Qualcomm say, I remember you were in the war room at Qualcomm and you know, doing all this stuff. And I said, yeah, I don't remember you there. And he said, well, I was back in the corner where it was dark, staying away from the fireworks. But I would go to Murthy's meeting several times after those, go to his room after those meetings and go through security to get there and all that. And I'd say, Murthy, I mean, the decision you made, you just threw away $50 million. And the response was, so what? That was a huge realization. Okay, to me, running in startups, $50 million was huge. But in these big companies, it's a drop in the bucket, and they're willing to risk that if there's a multi-billion-dollar deal on the other side. So it was, I think the biggest change is just the magnitude of the results from decisions that are made took a mental readjustment coming from small startups going to very large corporations. And that little lesson from Murthy has been valuable to me ever since.
So you got to learn and develop those skills and look at the bigger picture, the strategic things,
Yeah.
which we could easily miss in the startup world.
Yes, and I'm not saying it doesn't happen in large companies as well, because people tend to look down at their shoestrings and keep walking forward. But I think, you know, I think part of the value that I bring to Siemens is just that whole perspective. When I'm thinking about a strategy, I can think about it at the very high level, but I'm not comfortable with a strategy until I can map it all the way down into the ones and zeros and know what the sales channel looks like and know what marketing has to do and know what all those things have to happen in order to be successful with a strategy and with a new product rollout and all those sorts of things. And I'm finding that's relatively rare because people become so specialized now. It's difficult to see outside their own little world.
You are now working in a domain that is ripe for change. Elon Musk began that with the electric vehicle and bringing it into the market, making it mainstream. But I think we are a long ways off from making a full self-driving vehicle or a fully autonomous vehicle. What are the biggest challenges you see, David, to going from where we are today to a full self-driving vehicle or a full self-driving automotive system?
Okay. The technical challenges are not the biggest challenges. I'm not saying there aren't technical challenges that still exist, but I don't think they're the largest. Dealing with governmental bodies and regulatory institutions and things like that, they don't even understand what the technology capabilities are. So change there is really slow. And then the impact on automotive manufacturers to try to align with the direction that these government institutions are heading is a real challenge. And that puts into the system a lot of doubt, a lot of concern to slow things down, particularly the technology adoption cycle. The other thing that's been a hindrance so far basically goes back to several years ago at a conference. I don't even remember who it was. Someone from EE Times was talking about the hype curve for autonomous vehicles, and that there was so much excitement. Early announcements were made premature. Handshake deals were made with no substance behind them. And the whole world thought that we were on the path to fully autonomy and that surely it was only going to take another 4 or 5 years. That was probably 5 years ago. And that has caused several things to happen. You saw a lot of announcements made about joint ventures and partnerships and things like that, and many of those have not reached their full potential. Some of them have actually disappeared, even after billions of dollars of investment, because jumping on the bandwagon too soon without really understanding the complexities of what you had to deal with, not just technically, but culturally, governmentally, liability, all those sorts of things. And so we're still at a state right now where we're seeing progress technically, but the progress technically is happening with small groups working in parallel with the production teams that still have to crank out new model years every year and have to show an advancement in the right direction. And the real epiphany has been that we cannot incrementally improve vehicles to get to level 4+ and level 5. But instead, it takes really a real design. You have to redesign from scratch something that can handle level 5, even if you don't deploy it, but it's designed to handle that. And we've seen several projects like that using our technology moving in that direction. But the cultural, the internal fight, the pushback, the fear of, hey, if this is successful and I'm not in line with that, what am I going to do 5 years from now? So that is another hindrance to change. And it happens an order of magnitude more severely in automotive than any other industry we've seen go through the transition.
I hear you. One of the things I found very interesting about your career journey is that when you were at ARC, you said you got to know and became friends with people at ARM and at Tensilica. Normally, people view their competitors like enemies, you know what I mean? And like beat them up, or otherwise you're not going to win. How were you able to manage to become friends with your entire ecosystem, including your competitors?
You know, I say this often, and there's a former employee from Siemens EDA who's now at Synopsys. It was highly publicized, you know, and met him at APM last week, and we just sat down and talked for about 40 minutes. We are direct competitors. He manages the group that produces products that compete against what I'm doing, but that's all right. And there's room for both. And in reality, to solve these super complex problems, we need to collaborate more. We need to leverage each other's strengths to shore up each other's weaknesses, or we're not going to have a holistic solution. Because I like to say, you know, I spent 25+ years buying EDA and only a few years trying to be in the EDA industry. So I always position myself on the customer side of this thing. Whereas an awful lot of people don't look at it that way. They'll go into an account and say, here's, I have this widget, how many do you want? And I and my team go in very differently. We understand you have some challenges. Let's talk about those challenges. Let's talk about how what we can bring to the table here are some solutions to those challenges. And that might mean collaboration and cooperation with companies that we compete with. There's nothing wrong with that. It's all about delivering a solution that makes sense to the customer. And when the customer is going through the kind of upheaval that automotive is going through, they welcome that kind of approach. And that's what builds those relationships, because people move on. All right. You know, and there are people that I worked with at ARC, you know, that are very influential at ARM, and don't think that there aren't opportunities to take advantage of those relationships.
Mentor used to be a conventional EDA company along with Cadence and Synopsys.
Mhm.
And today it's a part of this giant Siemens. And there's so much vertical integration. Do you ever encounter the situation where you're seen as a part of Siemens rather than being an EDA company? And how does that play out when you deal with many of your customers?
Well, this is kind of where my marketing background helps quite a bit. You know, in one sense, it could be perceived as a hindrance, glass half empty. I prefer to think of it as a glass half full. And I approach it like this. So, you know, yes, there are challenges within a company the size of Siemens, particularly being in a digital industry software inside of digital industries, inside of AG. So there's several layers there. But the value that actually brings to our customer base can be represented in this way, in that Siemens has already invested, and this is public information, at least 10 billion euros acquiring companies. That if any of those companies haven't been acquired, Pave 360 itself and our solution for automotive digital twins that are holistic and mixed fidelity and all that stuff would not be possible. And there are an awful lot of companies out there that we compete against don't have that potential to get that kind of investment and integrate those companies together to pull together this complex solution space that we're playing in right now. So I see it as a major positive in the end. We were working on a project about a year and a half ago with a German OEM. And as I said earlier, we kind of put everything together and actually got the prototype in the vehicle. And we said, we need a track. Where can we get a track? And a guy in Wolfsburg said, we have one. It's like 2 blocks down the road. What, you already have your own automotive test track? Yeah, we do. So those are the kinds of things that, boy, they're hard to get otherwise, or you're waiting in line for 6 months for your turn. Instead, we just said, okay, well, let's schedule a date and off we go.
Not too long ago, we talked about the role of digital twins in making these kinds of complex systems, autonomous systems. And I know you've spent a lot of time thinking about it, implementing it. What role do digital twins have in this whole arena of creating complex intelligent systems going forward?
Well, I'm going to tell a little anecdotal story that really led to an epiphany for me. So I'm a big science fiction fan. I read science fiction almost constantly. And several years ago, I read a book about some deep space telescopes actually identified an alien armada heading towards Earth. And they had an AI that could take the data that it gleaned from this armada coming from it. In other words, we call it instrumentation data. It could determine that. And from that, it could create models of the ships in that armada, at least at a high level. And from that, it could deduce the right approach to handle the incoming armada. And I thought, no, wait a minute. So you have an AI that created a simulation. It ran simulations through lots of scenarios. And from that came an optimized solution to an incredibly complex problem that a human themselves would unlikely be able to solve, or would approach it in a very macho way and probably would have resulted in the Earth being destroyed or conquered. And I thought, that's an awful lot like what we did at NVIDIA and like some of the things we were trying to make happen at Qualcomm and the stuff that they've asked me to start looking at here at Mentor, now Siemens EDA. And so everything that I've done since then is around that. Let's build a system that initially a human can model these complex systems of systems and determine the behavior of things in a predictive way. In other words, with a particular configuration and a software workload, will that vehicle successfully navigate from point A to point B without any traffic infractions or running over dogs or baby carriages or anything like that? And then the next step beyond that, one would presume, was add the AI on top of that, which could be trained with information that's already available, so that we're not trying to train the systems we're producing. We're trying to train a system that's going to produce the right system. So it's a very different approach. And it all goes back to that sci-fi book that I read. I wish I could remember the name. It's been a while since I read it, but the concept has really stuck with me. And if you look at it in that way, then it's not just a simulation anymore, right? And when we start talking about fidelity and mixed fidelity and those sorts of things, we already have simulations that can very accurately predict power and performance, not just of a system on chip, but of the printed circuit boards, the ECUs or LRUs, and then putting them together on a network and then connecting many of those and then running scenarios through them. We're already doing all those things and collecting all that. So we can create a virtual vehicle now that represents what's going to exist one day, and real work can be done on it now. So waiting for the real silicon or real waiting for the ECUs or building a complex hardware in the loop system isn't really as necessary as it was. I'm not saying we replace them in their entirety, but the concept of shift left and starting very early in that process is a perfect fit for these complex systems of systems. And I like to call them intelligent vehicles.
Yeah, yeah. In fact, shift left has been there, as you correctly pointed out, at the subsystem or subchip level, SoC level, now going slowly into simulating things at the vehicle level. Do you think in order to have full self-driving, we'll also have to go beyond the vehicle into the environment, the ecosystem of the vehicle, the road conditions, and many, many more things like that?
No question. And that's already happening. So, we've partnered with the Siemens Mobility Group and trying to use the same kinds of simulations for smart city. So, V2X communications and rolling that in. We're starting to get into some technical aspects of this, but the bottom line is, when we first started tackling autonomous vehicles and perception systems and things like that, we had some very crude types of sensor fusion, only to learn issues with that type of solution. And then there are other types of fusions happening. And if you start talking about the smart city, integrating with onboard sensing, and then multiple vehicles with their onboard sensing and everything communicating, then what is it that you're actually fusing? And the latest path from what we're seeing right now is towards this concept of, you can call it object fusion. In other words, there's some abstract representation of something that is observed, whether it is by a traffic light or by a car around the corner you can't perceive, things like that. But how do you put that together? In the absence of that, then we're never going to get to the point where we feel confident that that vehicle that's driving us from point A to point B is doing a better job than we can do. The first time that it stops at a green light, simply because there's an ambulance coming that you didn't hear because you had your headphones on, then you start to think that maybe this vehicle actually is safer than it would be if I were driving myself. And that's going to take time, but it's going to take many, many proof points for the consumers to feel comfortable with it happening. There's just too many mistakes happening with the solutions that are out there today.
Wow, wow. It reminds me of ESP, the way things are happening, if it's done right, when it actually happens,
Yes.
will be like extrasensory perception. And what do they say? Any new technology is like magic, right?
Yes.
So
I think it's a lot like that. Yeah.
today, a lot of AI, especially generative AI, the kind of things you're talking about, creating new paradigms or doing things better than humans can do, has run into this problem called hallucinations. Is that a real risk when it comes to autonomous systems such as autonomous cars? Could they hallucinate?
Well, they do hallucinate right now. I mean, currently, depending upon, I should say, the complexity of the sensor arrays that you're dealing with, one great example of this is, again, we were working with an automotive OEM, and we were running through some scenarios in the virtual world, and we always hit this one scenario where a vehicle would come around a corner and just stop in the middle of the street for no apparent reason. It wasn't until we dug deep inside of what was actually going on, and we realized the fact that the vehicle was stopping because it thought there was a vehicle in its way when there was no vehicle. And then the question is, why did it think that? Well, we went back and looked at the scenario, and it was because the vehicle was actually heading towards a parking garage. And there was a curve before the parking garage, and it saw the vehicles in the parking garage and say, oh, there's a car, stop. So it wasn't smart enough to realize that it was looking at cars that were parked in the garage, and it was actually about 3 stories above ground level, and therefore it's not a concern to me because cars don't fly. So that's just one example off the top of my head, and there are many others about shadows and reflections and things like that, where it causes the vehicle sensors to believe that something is happening that really isn't happening. And that's sort of the superficial level of hallucination, and it can get much deeper than that based on a series of complex cascading events that happen that get the AI into the point that it thinks it knows what's going on, but it has no clue. And that's mainly the reason why we're seeing still too many accidents on the road with AVs.
Not only do they hallucinate, but sometimes they get phobic to crash on the third floor.
And
We'll have
actually,
to
that
get a
is
therapist.
yeah, I actually have in one of my older presentations a photograph in Silicon Valley of a man with a pistol pointing it at an AV that stopped in the middle of the road, backing up traffic for no good reason. It's just a representative of the frustration that people can feel. And that's just one example.
Yeah,
Another one is in San Francisco, is pretty famous, about the CEO of ARM and the CEO of an AV company in the Silicon Valley, and they were going for a test drive, and the vehicle wasn't allowed by other cars to get in the left lane so that it could make a left-hand turn, so it shut down, and they actually had to call out the IT department to come out and reset the car before it could continue driving. That doesn't give a lot of confidence to consumers.
yes, there's so much more to learn. There's so much more to automate. And hopefully a time will come when driving an autonomous vehicle will actually be much safer and better than what we are doing today as human beings.
It will, but it's not going to happen. It's not going to happen by driving billions of miles. It's going to
That's
happen by better engineering solutions that come out of the digital twin type solution. So we find these things earlier when they're easier to fix, much cheaper to fix.
In the good old days, there was this clear partition between hardware and software engineers. The software engineers are from Venus, they can do no wrong, and hardware engineers from Mars, they mess up in their chips. Do you see that kind of stuff happening as you bring all these parts together, from IP to SoC to chip to system to AI, all the way to smart cities? Do you see these little silos getting in the way?
Well, I have certainly seen that phenomenon many times at the past companies that I was with. And then the software team always gets pinched in the end, and they would have to come up with some sort of algorithm to kind of make up for the deficiencies of the hardware. And then it end up not reaching their frequency requirements. It could be something as simple as, a thermal sensor misplaced by a couple millimeters, that sort of thing. But one thing that we're trying to do is trying to eliminate that sort of siloing. And that's really a part of the digital twin methodology. Because when you start very early on and we're just sort of modeling the high level behavior, then that involves the architecture team, the hardware team, the software team, the systems team, and they're all sitting there. And as we increase the simulation's fidelity over time, that gives an opportunity, say, for the software people to say to the hardware people, hey, your document said this, but it's not behaving in that way. at one of the previous companies that I was at in Silicon Valley, I mean, that was the goal, to completely validate the software before you tape out the chip. And I think that's the direction that we need to go, not just on the SoCs, but we need to run production software very early. And that puts an emphasis on the IP selection. It changes the whole architecture. And I say system architecture, but there are many levels of system architecture. You have the SoC system, you have the software system, you have the ECU, the network, many different systems. And if you look at those at the system level, then it pulls those teams together, and it no longer allows them to be separate and siloed, where one team actually has to bear the brunt of mistakes that are made by another team simply because the complexity that they're dealing with. We often call that continuous integration and things like that. These aren't new terms, they're just applied to a broader, much larger solution.
In fact, I hear this all the time, especially from Tesla drivers, because they think it's an invincible vehicle. And in many ways, it may be that, oh, the next software patch, all the problems that we are having will be fixed. If that is truly the case, that with the software patch, you can, fix all the problems, do we really need to do what you're saying we need to do, which is have the production software be there along with the hardware and completely iron out things? Or can we
Yeah.
just fix it later in production or in the real world?
Okay, so this is the way that I see the industry heading. I'm sure you've heard of the SOFI consortium, right? Headed up by ARM. It's basically a framework for CI/CD. The interesting thing about that, when it's mixed with digital twins, what happens is the development teams as one will build a golden digital twin, wherever they are in that development process, hardware and software included. And that digital twin is capable of running through these complex scenarios. And then every engineer has access to their own virtual vehicle to do their development for that next day. They make the changes in their software using an agile methodology, and then every night they check everything in, and then they have overnight regressions. Think about what that means. Now you have hundreds or thousands of virtual vehicles running regressions overnight. Once those regressions actually pass that testing, then those updates get pushed to the golden model. And then the golden model pushes that result back down to everybody else's desk. They come in the morning and they have a fresh new vehicle with all the updates. You know what you call that after production? Over-the-air updates. But it doesn't happen at the end. It happens all the way through. So when OTA happens in a post-production environment, it's nothing new. It's been happening hundreds and hundreds of times already. And that resolves many issues. Things today often aren't designed to handle over-the-air updates. So companies like Tesla started with a blank sheet of paper, could plan that. But now if you're in this migration trying to go through levels of ADAS, trying to get to an autonomous vehicle, now you have a way to migrate those things into that bigger picture so that everything can be well tested, well in advance for over-the-air updates. So it's a part of the development process, not an afterthought.
So indeed, basically the way cars are designed today, the autonomous vehicles are designed today, is an agile process where every level of abstraction at some point starts getting tested, and you have many virtual vehicles that are being produced till you get to a certain degree of confidence. How do the regulatory agencies see this? Do they fully comprehend it? Because it's so different from the way
Yeah.
more than 100 years cars were designed or vehicles were designed.
Yeah, so that's called homologation, the whole concept of being able to show you're still safe after each one of these updates. And I mentioned earlier about governmental bodies and regulatory institutions. They only superficially tend to understand this. Of course, there's a wide spectrum of that level of understanding. But the concept is that if you could identify a set of complex scenarios that constitute correct behavior, then your regression tests simply include running through those scenarios and showing that that golden model, which one day becomes your production vehicle, still meets those requirements each step along the way. And I'm not saying everybody's doing that. I'm saying that's the holy grail. That's the direction that people want to go. Of course, different OEM and their ecosystems are moving at different pace to get there. But I think in the end, that's what it's going to take. And it's interesting. For a long time, we've had accident databases. Germany has one, China has one. There's GIDAS, there's JDAS. Different countries have their own, and it's like 5-7 seconds before an accident. And it's currently, the technology exists there today to take those actual videos of an accident and then generate a virtual scenario to push through the digital twin for each of those. So here's a concrete example. Germany has their own accident database, and it all gets digitized. And you say, Mr. OEM, you need to be past 98% of these tests to reach the alpha stage. And you need to do that in your digital twin each step along the way. Once you get to, pick a number, 99.9999% pass, then you show that the physical vehicle that you produced correlates to the digital twin you've been testing with all along. Once you've done that, then we'll let you put that car on the road. Then you know it's safe. You know that vehicle will handle all of those scenarios that are dictated by the federal government. And then we have safe, intelligent vehicles.
Can you educate a little bit more? Tell us a little bit more about PAVE 360 and how is the whole methodology different from how things were before?
Well, the big difference is that an automotive OEM would have tier 1 suppliers, and tier 1 suppliers would have tier 2 suppliers. Each of them have their own little black box. Tier 2 suppliers would produce a little black box. We call it an SoC. What's inside that? Only they know. But you need to work off a data sheet, integrate that into a printed circuit board, add some software onto that. Now you got a bigger black box. And then you pass that bigger black box to the OEM who tries to slap it all together. Okay, so now you have 50, 60, 100 plus of these black boxes called ECUs. You plug them all together, and surprise, surprise, it doesn't work. So that's what they call the integration storm. And they'll often tell me it could take years to get through an integration storm because everything is black boxed. There's no visibility of what's happening. So there's finger pointing. It's your problem. No, it's your problem. And there's no way to look into that other than your own stuff. And it's wrapped around a black box. The thing about a digital twin is there's really no need to divulge anything that is proprietary inside that black box. You provide the simulation of that black box so that people can start looking into it, collect the metrics, run different code bases, and in that way, you are integrating not just internally to a company and across the different divisions and across the skill sets, but you're doing the same thing with your suppliers as well. So the OEM controls their own destiny. Instead of taking what we can do, they're saying, this is what we need. So it turns the whole ecosystem upside down. And that's what's enabling the methodology. And that's enabling a lot of the change with companies like Qualcomm and NVIDIA and Samsung and ST and others actually getting into the SoCs, because now that whole ecosystem is upside down and turned around, and the OEM has more control and can dictate more of what happens. The suppliers that are traditional need to be reworked to accommodate that, and that's part of the upheaval. Some are moving fast, some really get it, they're hiring smart people. Others are taking a, well, let's wait and see approach. I wouldn't invest in those.
So, David, you have worked at various levels. You made chips, you made SoCs, you made systems, you worked in automotive, you worked in microprocessors, you worked in software, hardware, all kinds of things. Which part of your career have you enjoyed the most and why?
Let's just say I've not left any of those behind. I can still sling Verilog or write C++ on a regular basis. But what I enjoyed the most is probably what I'm doing now, because I think it really has the potential of making a difference. Several years ago, I was speaking at a conference on a panel, and an executive at a large automotive OEM came up and said, you know what, we need to work together because I think we can change the world. Kind of caught my eye. We've worked closely with that company for quite some time now, and it's really bearing fruit. I can't wait to tell the world what we're doing in that area. But I think the main thing is, I think we can really make a difference. We just need to stick with it, and we can make the world a better, safer, more renewable place by being smart and using technology to solve these problems. And hopefully in time, the cultural aspects will come in line.
And you know what, David? I've worked in other industries where regulations are very strong, just like in automotive, for the same reason, human safety and safety of crops, things like that. Industries such as in healthcare, both in the healthcare of human beings, healthcare of animals, as well as the health of crops, agriculture. Do you see this whole methodology that you folks are developing or have developed in the automotive space with Pave 360 and other things could be used in these other areas? Same thing in military aerospace and in many other areas. Do you think a similar methodology is already in place, or things can be learned from this domain into those domains?
Yeah, I was asked a similar question last week on a panel, and it was phrased as, this could be applied to so many different things. Why automotive? And they said, because it's the hardest. If we can crack this in automotive, then it can be applied to anything else. And we've already done prototype systems in healthcare, working closely with military defense and aerospace, and the list just goes on. And at the most basic level, you have the simulation capacity, the artificial intelligence, and then you swap out the sensing and the actuating, and it could be a heart monitor, it could be an autonomous vehicle, it could be, an intelligent plane, it could be any of those things. So yes, it can be applied. It's in the early days in many different industries, but it absolutely is the way to go forward with engineering in the future without any question in my mind whatsoever.
Indeed, you're working on so many exciting things. I can't wait to see the results and maybe participate in the whole process in which things are being made. Very, very exciting, to be honest with you. I
We
only
need to
need to
set up some
participate.
time and show you some of our demos. I think you'll be shocked what's actually
Yes,
possible. Most
yes.
people don't know. Yeah,
Let's do that in another interview. How do these things actually come together? Because we're
absolutely.
only talking, but it'll be fun to see
Love to do
actually
that.
things happening.
Yeah, would be
So
great.
again, thanks again, David, and to all those who are listening. We are living in a world that's changing super fast, and it's actually taking us human beings time to digest some of these changes, not just in the way things are made in engineering, but the impact it's going to have, whether it's just a chat GPT kind of software or autonomous vehicles on the road or new medicines with mRNA and other technologies. So please come forward. I would love to listen to you. I'd love to learn from you. And David, thanks again for giving your time to talk about these things.
Absolutely my pleasure. Thank you for having me.